Hi, I'm Vladimir from zkBob, and today I'm going to talk about the snark-based wallets. First, a couple of words about what is zkBob. It's a smart contract wallet that utilizes a Growth 16 proving system to enforce the validity of user balances. We'll talk a little bit more about which circuits, how it is used, in more detail later. But first, we'll talk about the Growth 16 itself. We've been in production for a year now, and I would like to share some knowledge we've gathered. First of all, a little disclaimer: this talk is intended for the audience of total beginners, whether you just know some school math and that's it, and you want to have a sneak peek under the hood of the mathematical techniques that are used to construct zk snarks and particularly Growth 16. So the problem is following. We have a program that requires too much resources to compute or may have some private arguments. And the prover wants to execute the program locally and present a proof to the verifier that will convince them that this execution was indeed correct. The third and maybe the most important requirement is that these verification step should take less time than the execution program itself, and the proof must be shorter than the program. This word shorter is indeed a rabbit hole of itself, and I don't want to get into too much detail here, but the idea here is that if you have a very big program, you wouldn't want to re-execute it, and you don't want to share all the parameters because the parameters itself can be very large. A very toy example of such a program can be checking the relation between sides of a Pythagorean triangle, where you have a public value of hypotenuse C, and you check that you know such catethi A and B, that their relation between, well-known relation between the sides holds, where A squared plus B squared is C squared. By the way, the problem of finding A/B is believed to be hard because it involves factorization of C. Of course, the problem of checking is easy, but it's very visual, and it will help us go through the transformation of this program step by step. So let's go. If you have ever used or seen any framework that uses for writing circuits for zk snarks, then the program would be something like this, and it's transposed quite literally in the code. Here's an example for the Fox crypto framework, but this talk will help you, as I said, have a sneak peek under the hood how this math is actually executed. So first things first, we create a so-called circuit. This is a structure where you have all the inputs, public inputs and secret inputs, on all the intermediary variables put together in so-called witness or assignment. And you have all the operations grouped into so-called gates, where you have multiplication gates and addition gates, and all the outputs are the result of a single multiplication between a left wire and a right wire, and arbitrary addition, multiple additions. So I would say that this step is kind of optional, and it is more of a mental exercise than it's useful for development. But the terminology used here, such as signals, gates, and circuit itself, is used throughout the industry, and it's basically in the Circum. It's very inspired by the electric circuits. So maybe it is helpful. The most important thing to notice here is that every output is the result of multiplication of the left wire and the right wire. Next, we'll transform this circuit in next concept called the rank 1 constraint system. It looks very busy, but in fact, it's pretty much the same thing, but in very sparse representation. You can see here that we have pretty much the same relation between the variables, such as a times a is a squared, b times b is c squared, and so on. But all the zero signals or zero inputs in every gate are more explicitly presented. What we do next is we can transform these equations into the table, which are, from my opinion, it's a little bit more visually understandable. So we see here is if any variable is whether a specific variable is involved in a calculation of a specific gate. For example, we see here that for the third gate, it's fourth gate, but with index 3, the variables a squared, b squared, the variable 1, which is default input, and c squared are involved, whereas a squared and b squared is left input summed, and c squared is the output. These matrices are like the essence of the program. It dictates how this program is executed and how the proof can be checked against. As you can see here, our relation between the left wires, right wires, and output are not satisfied here. So for the third gate, the multiplication doesn't give the expected result because it lacks the valid assignment. So let's recap what we've done so far. We had this circuit as a representation of the code itself, and we transformed it to 3 matrices of that show whether the variable is involved in calculation on a sorting gate. This is a common knowledge between prover and verifier, which is like a contract that will help them to generate the proof and to check it. Next, let's assume that we have, as a prover, have a valid assignment for this problem. So the catheta is 3 and 4, the public hypotenuse is 5, and other variables are 9, 16, and 25. And as I said, the default constant input is 1. So right here, we see that the relations now hold that 9 plus 16 times 1 is indeed 25. And it holds for every gate. Next, what we'll do now is we want to squeeze all the tables from the sides to make it a little bit more concise and easier for the verifier to check, because we want the verifier to do as less job as possible. So we moved from the element-wise multiplication of the scalar products to element-wise multiplication of vectors, such as the L to the right here. You can see that we just removed all the zeros from the table and summed up all the rows. I have conserved all the colors, so you see the 3 and 4 and 5, and 25 is the sum of 9 and 16. We will do the same thing with the right wire and output wire, and we'll see that the relation still holds, so all the multiplication are still valid. Why would we do that? Why would we want to have such a vector? This is because we can transform these vector of tuples into a polynomial. For example, if we interpret every tuple as a point, which is like a tuple of coordinates, we can create such a polynomial. This is called interpolation. It's a very well-known algorithm. It's very widely used. Here, the interpolation is made in real numbers, which is not the environment that we're working on. In fact, we're working in finite fields, and the polynomial, of course, would look quite different, but it suits our purpose of visualization. So let's recap once more. We had these three tables. We squeezed them to make it, three vectors, and we created three polynomials that have the same relations as before. Next, we define our main polynomial P, which is the result of subtraction between multiplication of left and right wire and the output. And our three polynomials are transformed to a single polynomial. And because our assignment is valid, and on every gate we had a 0, then our polynomial P must be 0 at all the gates, at each gate. And vice versa, we can say that if the polynomial P is 0 at each gate, then our assignment is valid. Why do we want to use the polynomial in the first place? Because polynomial have very unique and cool features, such as that we can determine a unique polynomial using the tuples, which we used so far. This is the interpolation. And if we have evaluations of two polynomial, then a polynomial which is the sum of them has the evaluation which is sum of evaluations. There are other very useful features that we will use later, such as that if the polynomial has a root, omega 0, then it is divisible by x minus 0. And also, the evaluation of polynomials is just a dot product of coefficient of powers of the variable. And also, two polynomials of degree d, such no more than d points. So we got one step closer. We had our circuit. We had transformed it to three polynomials, and then transformed it to a single polynomial with 0 at each gate. So our statement about the Pythagorean triangle transformed into knowing a polynomial such as this one. Of course, again, in finite fields it would look different, but it's pretty much okay and suffice for now. So since the P of x is equal to 0 at each gate, we can represent it as a multiple of something, some polynomial h of x, and all the monomial which look like x minus omega I, where I is represents all the indices of the gates. This product of x minus omega I is called the vanishing polynomial because it indeed vanishes at each gate. So our statement about the P of x being 0 at each gate can be formed into an existent of such an polynomial h of x, which is called quotient polynomial. Let's again reflect on what we've done so far. We had our circuit. We translated it into the tables of variable involvement. Then we had our polynomial, which represents the interpolation. Then we had transformed it to a polynomial which is 0 at all the gates. Then we transformed it to a polynomial h, which exists only if the assignment was correct. As you can see, this polynomial h gathers both the essence of the program because it was created using the matrices from the circuit, and it also exists only if the assignment was correct. So it has these both things. This is the Sage code, just if you're interested to reproduce the graphics. So how is it verified? So apart from the P being 0 only at gates, the divisibility property must hold everywhere. So we can also check it everywhere. So if we have a single point tau, we can check that h times t is indeed P, and that that would give us that the assignment was correct. The problem here is that if prover knows the point where this property is checked, then they can very easily cheat, because they can create such H so that this property only holds at this single point and nowhere else. And this way, the proof will convince the verifier, although the calculation was not made correctly, and it doesn't hold at each gate. So the problem is like, so we would like to make the tau random, which means that it is unknown for the prover beforehand. And then if it is indeed random, then the probability that it somehow got very lucky and that this equation will hold is 2 times d divided by p, because where we have d gates in the circuit and p is the number of elements in our field, which is a very low number. So the problem is, how do we make it this tau random and unknown to anyone else? Fortunately for us, the elliptic curve cryptography offers a way to encrypt values by multiplying a scalar tau by a point g, which is called a generator. So, and the problem of finding tau where you have g times tau is known to be hard. So the idea here is that if you have to calculate evaluation of a polynomial, you just make a scalar product of dot product of the coefficients and the powers of the variable. And now if we have the encrypted powers of variable, which is tau, so we have to calculate the evaluation at point g times tau. We just make the same dot product of the coefficients and the vector g times tau to the power of I for all the gates. So now we have to find this vector somewhere. This thing is sometimes called the trusted setup ceremony. In Zcash, that was even called the powers of tau. There is a project called perpetual powers of tau. So it boils down to lots of people coming up with random values, like as random as they can be. Then they calculate this vector of encrypted powers of tau, and all add these results with the previous contribution. So if at least a single contributor is honest and it discards all the values, after the procedure is complete, then this setup is believed to be secure. The result of such a ceremony is called a common reference string or a standard reference string, and it contains powers of tau and some other things that we'll talk later. This is the pain point of growth 16, and we'll talk later too. So after having the evaluations of our left, right, and output wires and quotient polynomial, we would like to check that indeed relation between them holds. But the problem is that we don't have such an operation as multiplication between elliptic curve points. But what we have is so-called pairings. It's a very complicated topic on itself. And the intuition behind it is that it's basically like an multiplication between encrypted values, where you can do multiply just 2 values and no more. You can just have multiple variables multiplied at one time. This is why we had these 2 multiplication wires in the first place. But also that would make if we would be able to multiply more than 2 variables at a time, it would also break the protocol, because we could make the a new proof based on an old proof without having to execute the program itself. So what we did here is that we transformed our program, which operated on Tau, to the encrypted version. We moved the output evaluation to the right-hand side, because subtraction in pairings is hard. So now we have just a single relation that a verifier needs to check, and that would convince them that the assignment was indeed correct. Now the whole protocol is the following. We create a proving key, which is a setup step, which is the powers of Tau and the encrypted evaluation of wire polynomials. And verification key is just the generator. Proving involves just calculating the encrypted version of calculating the polynomials for left, right, and output wires respectively, then calculating the quotient polynomial in a coefficient form, and then calculating its evaluation and sending all the left wire encrypted evaluation, right wire encrypted evaluation output, and quotient polynomial to the verifier. So the verifier can check just this single relation, and it shows that the assignment was correct. I would say that there are some inaccuracies here that was made by intention for the sake of brevity. Yeah. What do we mean so far? So we also, apart from being the calculation being correct at every gate, we also need to enforce that every single variable that is used inside the circuit was indeed the same. So we just didn't, for example, replace 25 with some random values. So this is why the not just the capital L evaluations are included in the proof, but we have to include in the CRS also the evaluations of the so-called apparent polynomials, little l, r, and o, which basically enforce that all the variables are indeed on their place. And this is the biggest problem of growth 16. I will talk about it later. We also have to ensure that the prover hadn't used any random values except the ones that were provided in the CRS. And this is why we have in the version of the protocol, we would have an extra step, which is called checking the alpha shift, where you have some more parameters like this, like random alpha multiplier, and you would have to check the relation between the evaluation of a wire and evaluation with the wire multiplied by alpha in an encrypted domain. I wouldn't say that it changes the protocol very much, so I have omitted it. Yeah. Also, we're working in a prime field module P, and also there are very few curves that are efficient for pairings, which are also called snark-friendly or pairing-friendly curves, and which is a very important thing to know from compatibility standpoint. Also, this omega I thing that we use to enumerate our gates is not just a regular natural numbers. They are indeed so-called roots of unity. It's a special number in multiplicative subgroups, where is omega to the power d is 1. So uh, these t polynomial is very easy to compute, and it also enables some optimization features such as fast Fourier transforms. Yeah, and one last thing is that public inputs are calculated by the verifier, but it doesn't make any difference also. Yeah, and you would ask where is the zero knowledge stuff, because we had these private inputs to the circuit A and B, and it seems that these inputs are somewhat leaked, because if we generated two distinct proofs for the same values, the verifier could find it out. So surprisingly, the zk stuff is optional, and it can be added as extension of the protocol. It basically adds some noise to all the variables. It's random variables that are generated during the setup phase and by the prover. And the idea is that you multiply or add something to the both right hand side and left hand side of all the equation, so all the relation hold, but the verifier doesn't find out anything about the initial inputs. Yeah. So how is it this protocol can be used in the wild? Since 2020, there is a dedicated precompiled contract on EVM chains with the BN254, also called alt BN128 curve, which allows efficient pairing. So you can basically write a smart contract that verifies a growth 16 snark, or not even growth 16, everything that uses pairing on this curve. We have a multiple of DSLs and frameworks and libraries that help you write a circuit like this. We are using zkBob, the Bellman prover, and for writing circuits, we use a framework called Folks Crypto, which allows you to both generate a Solidity contract as well as compile the prover to WASM, make bindings for Node.js and native native binaries also. So how can you use this? The most popular things right now, I would say, is the proof of set inclusion. You can basically do verifiable credentials, such as Polygon ID, or you can do something like a proof of reserves, which was, I believe, made by Binance to prove that they have reserves for all the client balances. Zcash also uses them for their sharded transfers, and of course zkBob also. The second thing is proving signatures, checking signatures. So you can prove the signature inside a snark, so without revealing the public key itself. And of course, you can check just arbitrary mathematical relationships. That balance is sufficient, or that the player has valid coordinates inside the game world, or anything else, as we have seen in our example. So a couple more words about how it is used in zkBob as an example of the snark-based smart contract wallet. So we have the transaction commitment, which basically has all the information about the transfer or withdrawal or the deposit that clients makes. And inside this circuit, we will do several checks. I think I have, yeah. So what we check is that if we spend or transfer the some funds, we check that ETHCC signature for the transaction was made correctly, um, without revealing the public key that the client uses. We check that the balance is sufficient, and we check that the account and the private nodes that they're using in transaction were indeed in the anonymity set. Yeah, this is how the basically the state of the application looks like. We have the private state that is stored on the client, which is like the lower thing, which basically is contained inside the transaction commitment. And we have a public state which consists of just Merkle roots and account nullifiers. And every time a transaction is made, we ensure that the commitment is correct. The sequencer includes this in their Merkle tree, and it accompanies the transaction with the proof of this correct inclusion. So we enforce that all the transactions were indeed included, and all the transactions are indeed valid. So about the growth 16 comparing to other protocols, there is a hallmark of the protocol, which is that you can check the validity of the huge program using a single curve point, which is encrypted evaluation of H, and that the proof is a constant size, and it requires a constant amount of operations. But it is also the oldest and the most battle-tested, I think, protocol. So there is quite a lot of tooling available, such as Circum, as I said, Socrates, Fox Crypto, ArcWorks, and so on. Cons. So yeah, the main downside of being able to check a single point is that the circuit is basically hard-coded in the setup phase. So every time you want to ship a new circuit, you have to do a new setup, which is basically very hard from security standpoint, because it's a big coordination problem. I don't know if it's good or bad, but like some users don't really care if the trusted setup was made correctly or not. I personally would like them to care a little bit more, but from the professional standpoint, the setup is a very questionable thing, of course. The other problem is the parameters. So the CRS is huge. It can be like hundreds of megabytes or even gigabytes. So it's not that critical if you have a beefy rollup sequencer, but if you force your user to do these parameters in order to make proofs, they can be a huge problem. Also, there are very few curves available right now. Maybe just on EVM chains or not, I don't know. For example, the BLS 12381 curve hasn't made it yet to the Ethereum. The EIP is stalled for a couple of years now. So there is only just one curve that is available on EVM. And this is the problem of all the snarks that use pairings. So what's in terms of adoption? I would say that if we assume that the privacy is required from us adoption, then it's basically done, and we have an application that allow users to transact in private. But also there are much more than to be done. Basically, we want these private applications to be able to cooperate with other applications and institutions. the UX must be really good and for the users to move from the Web2 applications to the crypto. And also there is like a gray zone right now whether we have to disclose some information about these transfers or not. So some more details about these. So the main problem with UX is that the bigger the circuit is, the longer it takes and the more resources it takes from the prover. And it's very crucial for mobile users. And I would say that it also applies to using hardware wallets, of course. And the main bottleneck here is so-called multiscalar multiplication, which is researched quite actively right now. And there are certain directions, such as from engineering standpoint and from theoretical also. Quite a few words about this. If you remember, we had these multiple polynomials for left, right, output wires and quotient polynomials that we had to basically evaluate in the encrypted domain, which is the dot product. And this dot product thing scales really, really bad. And group operations, which is multiplication by of the point of scalar, is kind of hard. And the problem is that we have to do it lots of times. And there are certain approaches that can be adopted, such as one of the most popular is so-called bucket adding approach, where you can basically divide your 256 bits numbers into lower bit limbs, like 13, 16 or something like the bits. And then it creates so-called buckets where you these every limb has only 2 to the power c possible values. So you just throw some of these points into a respective bucket. Yeah, another problem is the UX and composability problem is that the address system between the Ethereum and private wallets is non-compatible. So you cannot use, for example, the centralized exchanges to withdraw money or fund or deposit the money. And also because of the many incompatibilities, you're forced to use the DApp itself to store your private data and keys. So I hope in the near future, wallet extensions such as MetaMask Snaps will help at least with the problem of the storing securely the keys and data. And we will see in the future also if the problem with addresses and compatibility will somehow solve. Yeah, another problem is that there are lots of cryptographic primitives out there used for mostly authentication, such as ED25519, which is used in lots of protocols. And for example, WebAuthn cannot be used inside the snarks. So, for example, for the signature in check in zkBob, we use a dedicated curve introduced also by the Ethereum Foundation, which is called Baby Job Job. And it's a special kind of curve that could be used inside the snark. And most of the other curves are not that efficient to use. There are some gadgets that you can write to work around the things like this, but it's very inefficient. unfortunately. Yeah, another problem for private wallets is the state synchronization, where if you have a collection of private input, you have some history that is stored on chain. There is no way to somehow fetch it in a single request, because you would compromise your anonymity. So you either have to brute force, like try to decrypt or something, like transform and find out if it is yours or not, or you have to trust some third party. And unfortunately, I haven't seen any progress with this thing, although there are some um, papers which try to use fully holomorphic encryption for the things like this. There is no practical thing that could help, as far as I know. So, and the individual problem of the growth 16, and for us, is that shipping new circuits is really a pain point. And we have just 3 circuits, and introducing a new one is always a huge problem. And I hope that the system, like Blanc and all the flavors of Blanc, will get better throughout the years. And I also hope that some system that introduce recursive proofs, so that you can have not that lightweight verifier as in Growth 16, but it is deployed not on the mainnet, where the verification can be very costly, but it is deployed somewhere on L2, and it's the proofs are aggregated or folded so that it costs less. Yeah, and the last, but not least, there is a problem with privacy application, that we don't have certain requirements about what private arguments, what private data has to be disclosed or what is not. We have our view on this problem, of course, and we have special opt-in compliance features, such as a compliance report, where you can decide to disclose only a certain period of your transaction history without compromising nothing that is outside of this period. There are also other approaches, such as privacy pools, that use these externally provided association sets, so that you can prove that your funds were indeed one of the checked deposits, and not associated with hackers, for example. There are also some very interesting solutions that are being developed last years, some like Polygon ID, which is privacy preserving verifiable credentials, that also uses Growth 16 and Merkle trees. So this is it. There are some links with interesting materials about the Growth 16 and not, and of course about zkBob. Thank you.
Yeah, awesome presentation, Vlad. We still have a couple minutes for sure, so I'd like to ask some questions about some things that caught my eye, and I'm sure Rob is, being a mathematician and math degree guy, he's probably itching at the chops too, but I just want to go first because I know that you guys are going to take it over after. So on the slide on circuit and transaction commitment, I've been doing quite a bit of research into the world of, I think it's the slide right before the circuit and Merkle root one. So it's towards like the second half there.
Okay.
Pull it up. Yeah.
Okay.
I've been doing. Yeah. It's it should be just right after those ones.
This one, right?
So I've been doing quite a bit of research on sequencers and kind of how their costs of rollups work, kind of what the business model is, how they operate. And so based on this operation here, basically what we have is that there's a new transaction being created, and it basically being verified that it is indeed correct. And so coming on to the next slide, we have that sequencer proves that this new Merkle root is indeed correct and corresponds to that set of commitments. Now, in this part where it says to help offload part of the work from the contract and client, is that an economical reason? Is it a technical bandwidth reason? Is it because you can store that data off chain? You don't have to pay to store it on chain. Kind of what is like the reasoning behind?
Multiple reasons. Yeah. Okay. There are multiple reasons. First of all, the sequencer eliminates the race condition between different clients, because if there were no sequencer, then the sequencer is like a point of synchronization between clients. Otherwise, like two clients that would try to create the proofs for the same Merkle root, they would create like a race condition, and the person who posted it, then they would, of course, get in the conflict with each other. Other than that, of course, there is an optimization thing that we don't want this thing to be calculated on the client also. And the third thing is that we don't want the tree itself to be stored on chain. We want to in the calculation of the Merkle root, we don't want to do it on chain, because we use the Poseidon hash because it's a snark friendly thing, and it's rather expensive to calculate on chain, because it involves it includes also hard operations, I would say. So TLDR is that it's expensive, and it requires more storage, and it also creates a race condition.
Yeah, makes sense. Block space is valuable. Thanks for the answer. Pass it over to Rob.
Thanks. Great presentation, Vladimir. My question is about the multi-scalar multiplication. You mentioned that accounts for 80% of the computation in the proof. So this is like the moon math that everyone talks about. Like, this is the zkProof moon math that everyone just kind of like trusts but doesn't really verify. And I think part of the reason of that is because it's like complex and it takes a lot of computational work. So my question is like how this applies and how we can choose an elliptical curve that makes the most sense for this moon math. Like you mentioned, I think it was BLS, and you mentioned a few curves. There's a few of them out there. Like, why do we choose certain curves for certain reasons? And is there like a general purpose, or is it more of a specific purpose on why we choose certain curves? And then where do you think like that direction is going?
So first of all, the MSM thing itself is not that I wouldn't say that it's complicated. All the like algorithm are pretty simple, but like the question about the curve is kind of tricky. So there is a question of security, of course, and there are certain teams and researchers that create and find out all these new curves, and this is like a bottomless rabbit hole of its own. It's a very complicated thing. There is a very concise tutorial about the BLS 12381, and you can search it, which is called BLS 12381 for the rest of us, and it's a concise form, but you can estimate how hard it is like to find and estimate security of the thing. So yes, different curves have different properties. Like for example, these curves have are pairing friendly, which means that they have like some thing like curve extension, embedded degree, or something like this. This is like indeed the Moon math, and BLS also has this property of which is called like endomorphism, which is can be used to make the MSM much more efficient. And unfortunately, it's not, as I said, it's not supported by EVM right now, but only the BN254 is supported, but it doesn't have this endomorphism feature. Basically, what is endomorphism is a way to better predict what would be a result of multiplication of scalar by a point, because on the most of the curves, it's a completely random thing, which is how this was invented in the first place. And there are certain curves where it is not so much random, and you have some pre-processing thing that can speed up the MSM, but unfortunately, none of them are right now supported. Like again, TLDR, nothing is static, and we will see more curves later, and we will see more curves, I believe, supported by the popular blockchain platforms and networks. And I think the initiatives like zPrice that pays a huge amount of money for speeding up the MSM, and also other approaches as well, is helping also. Yeah.
Amazing. Cool. Makes sense. And there's blockchains like Zcash that have used like certain elliptic curves, and then like you said, there's multiple blockchains that use multiple different curves for multiple different reasons, and we'll continue to see more chains and more curves for their use cases.
Yeah. Zcash team is, as far as I know, the Zcash team invented some, maybe like just a new family of curves for their future upgrade to Halo 2. Halo 2 is like the next thing from the same team that come up with the sapling protocol, which is what is Zcash based right now. It's transparent Zcash snark, which means that it doesn't need the trusted setup ceremony, and it still has very nice features for standpoint of proof size and verification time, but they have they have these nice new curves which are not supported in else, but maybe that will change in time.
Yeah, I'm curious to see if they can integrate somehow with some of these other curves that are more popular and widely adopted on Ethereum. We'll see. We like the curves. Thank you so much for coming on, Vlad. It was a pleasure.
Thanks,
very, very insightful and learned a lot. Thank you.
Thank you.